Hello, I'm Klára Janušková, the first author of the Text Recognition, Real-World Data and Where to Find Them paper. Scene text recognition is an essential part of reading systems. State-of-the-art methods, based on deep neural networks, require large amounts of annotated data. Because of the lack of real-world annotated data, the field heavily relies on synthetic images. There is another option, so far unexploited. Annotating is costly, yet many images with text metadata are available. For example, given a photo with its GPS coordinates, one can search for nearby businesses in a service like Google Maps. The results often contain the name of the business, the name of the street, the house number, as well as other information. We propose a method that exploits images accompanied by a list of texts that have a high probability of appearing in the image. Such texts are called weak annotations. The core idea of the proposed approach is to associate the output of the detector and the recognizer with weak annotations. The resulting set of text detections with weak label transcriptions is called pseudoground truth, PGT in short. The PGT is added to the training set to fine-tune the recognizer, whose output in turn updates the PGT. The method is initialized by training a detector and a recognizer on fully annotated data F. The PGT generation method then turns the output of these models on weakly annotated images into PGT. In each iteration, the recognition model is fine-tuned on the union of F and the PGT from the previous iteration. The PGT generation method works with the new recognizer, keeping the detector from the initialization step. The two steps are repeated until convergence. For each image, the PGT generation method first obtains text detections and its corresponding text transcriptions. Then, a mutually nearest weak label assignment algorithm is performed to obtain a set of PGT candidates. First, for each detected text, the algorithm adds an edge to the closest weak label using the normalized edit distance. Then, the algorithm repeats the procedure in the opposite direction. If the detection and the weak label texts are mutually nearest, they form a PGT candidate. Each candidate consists of a bounding box, a detected text, and a weak label. If the detected text and the weak label are the same, we assume the original bounding box is optimal and contains the weak label and becomes PGT. If not, we attempt to find a new bounding box, minimizing the edit distance by a neighborhood search. If the original bounding box is extended to the right, the edit distance between the weak label and the text in the bounding box decreases. The same happens when we shrink it on the left. If the distance between the recognized text in the optimal bounding box and the weak label is lower than the threshold, and the first and the last letters agree, we assume the bounding box contains the text from the weak labels and becomes PGT. We tested the method on two datasets. The Amazon book covers dataset, where the author and the title of the book serve as weak annotation. The other, the UberText dataset, is fully annotated, but we ignore text locations to simulate the weakly supervised setup. This allows comparison with fully supervised learning. After 6 iterations, the method outputs about 110,000 PGT instances on UberText and close to 1,600,000 instances after 3 iterations on Amazon book covers. The red columns show the number of instances obtained without the neighborhood search, which is significantly lower than with the yellow columns depicting the PGT instances added by the neighborhood search. The accuracy of the PGT was manually verified on 500 samples from each dataset. The false positive rate was 4.1% for UberText and 2% for Amazon book covers. In UberText, some are due to wrong annotation. PGT images generated on UberText contain artistic fonts, perspective deformation, and curved or blurred text. Evaluated on the UberText test set, the accuracy of the recognition models trained with the UberText PGT increased in each iteration until convergence in the 6th. From bottom to top, the red line shows the performance of the baseline model trained with synthetic data. The orange a simple pseudo-labeling approach without weak annotations. The cyan the model trained with PGT obtained without neighborhood search, and the green the fully supervised learning. The recognizer trained with PGT from both datasets was evaluated on 7 benchmarks. Training with PGT improved the word accuracy on all of them by 3.7% on average. Many of the images where the model improved contain a lot of noise, difficult fonts, or occluded texts. The images where the performance got worse are often challenging even for humans. Other methods report the results on alphanumeric characters only. We trained the PGT model without punctuation, depicted in red, and compared with the state-of-the-art results, in green, and the second best, in blue. On multiple datasets, our single model either surpasses or matches the performance of the second best methods. Note that the state-of-the-art performance is achieved by multiple different methods. Thank you for your attention.